MultiScan incorporates more than 15 new and patented technologies to enable automatic radar operation. But the four major ones we will examine here are beam-to-beam power comparison, automatic temperature-based gain, geographic weather correlation, and track-while-scan capability. But before we describe these technologies, let's talk about the technical obstacles that must be overcome to build an automatic radar. So here's a question. When a radar beam paints a target, does the return contain discrete digitized data that can be separated into different components, like terrain and weather? Or is it a single energy pulse that is composed of all the data painted by the radar at a particular range? The answer, of course, is that it is a single pulse that basically says there is something or some group of things at a particular range. And if you remember from Module 1, it is a pretty wide diameter pulse as well. When operating the radar manually, one method for distinguishing between ground clutter and weather is to raise the tilt to reduce the clutter. Unfortunately, this also tends to reduce the intensity of the weather return and limit the range that weather can be seen. In addition, with certain types of terrain, such as the cliff face displayed here, very strong returns can show up further out on the edge of the beam and unexpectedly introduce ground clutter into the picture, even with a high tilt setting. Cities are even a greater problem because man-made structures are very strong radar reflectors and again introduce clutter into the radar return. The original technological breakthrough for MultiScan was beam-to-beam power comparison that enabled the radar to eliminate ground clutter. MultiScan eliminates ground clutter by first using an internal terrain table to draw a line that is conformal to the Earth's surface. The radar then sweeps the area in front of the aircraft at a predefined tilt angle that is dependent on the height of the terrain. Returns are stored in a temporary memory buffer. A second sweep is then conducted at a slightly higher tilt angle. If we examine the exact same returns from the first and second sweep, we will discover that they have different strengths or power due to the different tilt angles. By doing a power-to-power comparison, it is possible to determine if a return falls below or above the conformal line. Returns that fall below the line are eliminated as ground clutter. Returns that are above the line are considered to be weather. This method of ground clutter removal also has the benefit of removing clutter caused by challenging terrain and cities. This picture shows the difficulty of distinguishing ground clutter from weather at longer ranges, even with the use of excellent manual operating techniques. In auto, MultiScan uses the beam-to-beam power comparison to eliminate the ground clutter, and the weather is now clearly visible. Once MultiScan has eliminated the ground clutter, all the weather in front of the aircraft is stored in the memory buffer. However, if all the weather was shown, it would result in many unnecessary deviations. So the radar uses the same beam-to-beam power comparison to measure cell height and determine the cells that reach the aircraft altitude. In this case, the radar draws a line that is approximately 6,000 feet beneath the aircraft. This is a curved line that conforms to the curvature of the Earth. In a similar manner to the way the radar removes ground clutter, an initial sweep records returns and stores them in a temporary memory buffer. The second sweep at a different tilt angle then enables a power-to-power comparison to see if the top of the cell falls above or below the line. The radar then chooses to show only weather that is at the aircraft altitude. This quiet, dark cockpit concept is designed to reduce crew distractions and prevent unnecessary deviations. If only the edge of the beam were used to determine cell height, the effective range would be limited to 40 to 60 nautical miles. With MultiScan's beam-to-beam power comparison, cell top measurements begin at 120 nautical miles, with a goal of an accurate display of threat weather that is at the aircraft altitude by 80 nautical miles. These pictures show the end result. Note the weather at 30 and 70 nautical miles. And also note the weather coming onto the display at 180 nautical miles. And finally note that the low-level weather is not displayed. In actuality, accurately determining the tops of cells is more difficult than just measuring cell height due to the fact that the tops of most cells are non-reflective and also because of the variable nature of weather around the world. So let's examine some of the weather science that must be considered for accurate cell top measurement. First, let's look at the composition of a typical thunderstorm. Thunderstorms can be described in two ways: what you can see with your eyes, what is visible, and what the radar can see, what is reflective. The tops of thunderstorms are composed primarily of ice crystals and are poor reflectors of radar energy. Thus, thunderstorms have both a radar top and a visual top, and the two are seldom the same. In the case of growing storms, the extent of the thunderstorm threat extends well above what the radar can actually see, and includes both the cell top and the turbulence bubble that is pushed above the growing cell. Automatic temperature-based gain is the first technology that is used to deal with non-reflective cell tops. You'll remember from Module 1 that automatic temperature-based gain increases gain as the outside air temperature decreases. Thus, at cruise altitude, manual max gain and auto cal gain display similar results. Essentially, this reduces the non-reflective portion of the cell so that more of the actual cell top is visible to the radar. Remember from Module 2, what does green mean? That this results in more energy on target at cruise altitude than most pilots are used to seeing. Please review Module 2 for proper radar interpretation in light of this increased gain. Let's also look at how weather varies based on geography to understand the third technology, geographic weather correlation. Scientists have long known that thunderstorms display very different characteristics depending on where they are in the world and whether they develop over land or over water. For instance, a typical Central African cell has very strong updrafts that carries water content to high altitudes. These cells also exhibit significant convective activity well above the freezing level. A Central Pacific cell, on the other hand, might look very similar on the outside, but its internal characteristics are vastly different. Updrafts are not nearly as severe, and thus high-altitude moisture content is far less. And most convective activity is much closer to the freezing level. This chart is one of many by Dr. Ed Zipser, one of the world's leading climatologists, that depicts the worldwide variation in thunderstorm development. Note that continental land-based cells have strong reflectivity characteristics at cruise altitudes, while oceanic cells have very poor reflectivity characteristics. Equatorial land-based cells fall somewhere in between. Note these weather pictures and how closely they correlate with the chart. The right-hand cell has significant convective activity and provides excellent reflectivity characteristics. In contrast, the oceanic cell on the left has much less mass and much lower reflectivity. The green, yellow, and red colors at the bottom right-hand corner of the chart equate to the standard radar reflectivity levels. Note that if the radar is set up for proper weather detection of this continental land-based cell, it will show up on the display as yellow or red. However, if radar settings are not adjusted to account for the different cell characteristics over the ocean, then the cell will not even show up on the ND. The problem is made even more difficult due to the fact that these regional variations in weather change depending on the time of year and the position of the ITCZ, or Intertropical Convergence Zone. In recent years, scientists have used new weather satellite systems to analyze and catalog tens of millions of data points that have enabled us to develop robust geographic weather models for weather around the world. MultiScan incorporates these weather models into a worldwide database that resides inside the radar. Using a 10-degree by 10-degree geographic grid, the radar sets thresholds based on geographic position, time of year, and whether the aircraft is over land or water. In regions where thunderstorms exhibit very poor reflectivity characteristics, thresholds are set low so that when the radar detects moisture at lower altitudes, it can predict that the cell top reaches to the aircraft altitude. In regions where thunderstorms display strong reflectivity characteristics, thresholds are set higher to prevent the radar from overwarning and causing unnecessary deviations. Thus, thresholds are matched to weather characteristics in a particular geographic region to determine the actual cell height and to best display the actual thunderstorm threat. Finally, MultiScan's new ThreatTrack features are enabled with the Rockwell scan technology that tracks up to 48 thunderstorm cells while scanning the area in front of the aircraft for additional threats. The radar determines each cell's relative threat and then schedules individual cells for detailed analysis in order of threat priority. The vertical sweep used by the radar essentially produces a nowcast of the storm's relative severity. Essential elements that are used in the threat evaluation include severity and height of the convective activity in the cell, temperature, cell growth rate, and upper-level winds. This analysis then enables the directly measured and inferred MultiScan ThreatTrack features described in Module 3. In summary, MultiScan ThreatTrack radar contains a decade's worth of technologies that drive the radar. But the four fundamental elements are beam-to-beam power comparison that enables ground clutter removal and cell top measurement, automatic temperature base gain that allows the radar to better see non-reflective cell tops, geographic weather correlation that enables the radar to better predict actual cell tops in the different regions of the world, and Rockwell scan technology that enables detailed thunderstorm analysis and activates the ThreatTrack warnings.